Okay, so in this video, I want to have a look at solving a second-order differential equation, non-homogeneous, with a sinusoidal step input. So the input is going to be a sine wave, but it's only going to begin after 2 seconds, after t equals 2, if t is the second is defined in seconds. So let's have a look. And we're also told in the question that the initial conditions are such that the function is 0 when t equals 0, and the first derivative is also 0 when t equals 0. So let's dive in and have a look. So we've got the equation here as f double prime t plus 5f prime t plus 6f of t equals u t minus 2 sine t minus 2. So we've got the input as a standard product of a function and a Heaviside step input. So what would be nice to do is that once we solve this, we can plot this on Matlab and actually see the step input and then see the response. I think that'll be quite interesting, and then we can maybe get some kind of an idea, or maybe make a guess over what kind of dynamical system this will represent. This could represent in real life. So, so just to get some kind of an idea of what we're dealing with here. So, if we draw the input, just to get an idea of what the input is. So, sine t minus 2 is going to be something like this, and obviously it's going to extend like this as well, this being t equals 2. And the step input dictates that the function only begins when t equals 2. So the actual step input is going to look something like this. Okay, and it's obviously going to continue. But the point is it only begins over here. So this whole right-hand side is really sine t with a c shift of 2 for t is greater than 0. Because remember, if we were to plot what sine t looks like, it's going to look like this, isn't it? For t is greater than 0. And if we shift that entire thing 2 units to the right, we're going to end up with the red line starting when t is 0. So that's why it's 0 before t equals 2. So at least we have an idea of what the step input looks like. And it'll be interesting to know what the response is, which is hopefully we're going to find out. So if we just say f of t equals x for the purpose of solving this, I should say let f of t equal x. And then we can say that x double dot plus 5x dot plus 6x equals u t minus 2 sine t minus 2. And if we take the Laplace transform of the entire left-hand side, and we take the Laplace transform of the entire right-hand side, they're going to be equivalent. And the principle of linearity obviously states that the Laplace transform of summations of components are going to be equal to the Laplace transform of each individual component summed together. So we can say that this is going to be equal to the Laplace transform of x double dot plus the Laplace transform of 5x dot plus the Laplace transform of 6x equals the Laplace transform of u t minus 2 sine t minus 2. And we said before that the Laplace transform of x can be called x bar. The Laplace transform of the first derivative will be sx bar minus x naught. The Laplace transform of x double dot, the second derivative, is going to be s squared x bar minus sx naught minus x1. And while we're at it, we can say that the Laplace transform of ut is just going to be 1 on s. The Laplace transform of ut minus c equals e to the minus cs on s. And the Laplace transform of ut minus c, f of t minus c, is going to be e to the minus cs f of s, providing that the Laplace transform of f of t equals f of s. It's really important to commit these to memory. So it's really, really intuitive, these things. They have to be very, very intuitive to be able to see these transforms, and obviously to be able to see the inverse transform as well. So whenever I'm doing a question, I always write out these transforms just to reinforce what they are, because they just need constant reinforcing. So it's a good opportunity just to write them all down again. So now we can say we can make the substitutions, and so let's go ahead and do that. So we can say the Laplace transform with the second derivative is going to be s squared x bar minus sx0 minus x1, and from up here we can say that x1 equals x0 equals 0. So we can say s squared x bar minus s0 minus 0 plus 5x dot, which is going to be s x bar minus 0 plus 6x bar equals the Laplace transform of ut minus 2 sine t minus 2, which is going to be e to the minus 2s dot f of s, and we know that f of t is sine t, so the f of s, the Laplace transform of sine t, which is the function here, so the Laplace transform of sine t is going to be 1 on s squared plus 1 squared. Okay, so now we have our non-homogeneous second order differential equation with sinusoidal step input at t equals 2 in the form of a Laplace equation. So let's solve the equation for x bar, and then once we have a nice equation for x bar, which is f of s, we can then find the inverse transform of f of s to find f of t, which is the function that we're trying to find. So let's go ahead and take out x bar. So we're going to have s squared plus 5s plus 6 equals e to the minus 2s on s squared plus 1. Yeah? I'm just going to move this all the way up. And now we're going to divide both sides by s squared plus 5s plus 6. So we can say now that x bar equals e to the minus 2s on s squared plus 1 times s squared plus 5s plus 6. And we should be able to see that this is going to be equal to e to the minus 2s. S squared plus 1 is a non-reducible quadratic factor. And then over here, we should have s plus 3 and s plus 2. 6 and 3s and 2s, yeah. So now what we can do is try and find a way to put this into partial fractions. So let's go ahead and do that. So we can say x bar equals e to the minus 2s. 1 on s squared plus 1, s plus 3, and s plus 2. So we can say, therefore, that that's going to be equivalent to e to the minus 2s, e to the minus 2s, a, s plus b on s squared plus 1, plus c on s plus 3, plus d on s plus 2. Yep. So let's go ahead and just find the coefficients for the partial fractions over here. And there we have the expression for x bar, or f of s, in terms of its partial fractions. So, in terms of the coefficients of the partial fractions. So let's take out 1/10. And I think this will look a lot more, a lot less intimidating once I do that. So let's take out e to the minus 2s, 1/10. So we can say minus s plus 1 on s squared plus 1 minus 1 on s plus 3 plus 2 on s plus 2. And now what we need to do is bring in the e to the minus 2s again to all the terms. And we should be able to see something that looks like the second shift theorem going on. And again, to know to do that, just to put that back in, is just from experience, really. And if you're if you've got the second shift theorem very intuitive in your mind, you'll find it easier to recognize that you need to have an e to the minus cs dot something else, and that dot something else is the f of s, which you can then find f of t, and then find a Heaviside Step product with that. So let's go ahead and do that. So we can say 1/10 minus e to the minus 2 s s plus e to the minus 2s. Be very careful here. Is that right? E to the minus 2s. Yeah. Okay. All on s squared plus 1 minus e to the minus 2s on s plus 3 plus 2 e to the minus 2s on s plus 2. And then let's bring this into its component parts. So we can say e to the minus 2s dot s on s squared plus 1, that's a minus, and that will be the first term, plus e to the minus 2s dot 1 on s squared plus 1, the second term. So I've just split that up into two parts, minus e to the minus 2s dot 1 on s plus 3, plus e to the minus 2s dot 2 on s plus 2. And now this is starting to look a little bit more friendly. So if we were just to state the second shift theorem again, so we've got it over here, we can say the Laplace transform of u t minus c, f of t minus c. So I'm just getting a warning saying my disk is almost full. Hopefully it's still going to record. Equals e to the minus cs f of s for the forward transform of f of t equals f of s. So we can say that that's going to be, we can now say that x is going to be equal to 1/10 of e to the minus 2. So we've got a minus u t minus 2 shift going on. And if f of s over here is s on s squared plus 1 squared, we should be able to see that that's going to be equal to, the f of t will be the cosine t function. Yeah. And there's a shift of 2. So that will be u t minus 2 cos t minus 2 plus u t minus 2. And this will be sine t minus 2. Remember, the function is sine t here, but there's a shift of 2. And then we can say minus u t minus 2. And the function, if f of s is 1 on s plus 3, we know that this is going to be e to the minus 3t, and that has a shift of 2, so it's going to be e to the minus 3t minus 2. And then we're going to have plus u t minus 2, and then the function is 1 on s plus 2, which will be e to the minus 2t, and the shift is 2, so we'll replace the t with t minus 2, and then there's a linear factor of 2 here, so we'll put 2 over here. And then what we can do, we can take out the ut minus 2 and say that, we can say that f of t equals 1/10 dot ut minus 2 minus cosine t minus 2 plus sine t minus 2 minus e to the minus 3 t minus 2 plus 2e to the minus 2 t minus 2. And that's our final answer. Okay, so here we have a Matlab plot of the input of our function, which was ut minus 2 sine t minus 2. So what we can see is that the input is 0 up until t equals 2, and then the function turns on. So effectively what we have is sine t just shifted 2 units along the t-axis for when t was greater than 0 originally. Now if we increase the number of cycles of the input, we can do that over here with the slider, and we can see the input change. So now we have 5 cycles, so that will be 5 times 2 pi over here, plus 2, and actually minus 2, but we can see that the input doesn't change before t equals 2. When t is before 2 is 0, and then it turns on. So that's the beauty really of the Heaviside Step. And obviously, if we wanted to switch off the function at some point, we would just subtract. U minus alpha at any time point we wanted to turn it off, sine t minus 2. And then that would effectively turn the function off. Now let's go back to 2 cycles, and let's go to 1 cycle. And what we're going to do is turn on the response. So now if we do that and go back to 1 cycle, there we have the response, which was the function that we actually derived, which was 1/10 dot ut minus 2, and then the rest of the function, which is really nice. So we can see that the function is only turning on at t equals 2. And then if we increase the input for, say, 7 cycles, 6 or 7 cycles, we can start to see what the long-term response is actually going to look like, which is really nice. Let's go back to, say, 4 cycles. So we can see that the response is a sinusoidal response. And then if we increase it significantly, let's say to 13 cycles, we can see what's happening. So there's a lot of amplitude suppression. And if we increase a little bit more just to see the trend of how the response is changing, I don't know if it's just me, if there's a slight oscillatory motion in the general pattern of the response. And let's go all the way to 50 cycles. I set the limit at 50 just because of the mains UK supply being 50 times a second. And then we can see, so the blue line being the input and the red line being the response, which is really nice. And that's how we solve a second order non-homogeneous sinusoidal step input using Laplace. So I hope you enjoyed that.